Alright, so in this lecture I'm gonna be talking about another approach for sentence embedding, which is called self-contrastive decorrelation, SCD, this paper in 2022. This model, clear in 2020, employs multiple sentence level augmentation strategies to learn a sentence representations. Despite the simplicity of these methods, they require careful treatment of negative pairs, relying on large batch sizes or sophisticated memory strategies. These include memory banks or customized mining strategies to retrieve negative pairs efficiently. In NLP specifically, the endeavor of hard negative mining becomes particularly challenging in the unsupervised scenario. Increasing training batch size or the memory bank size implicitly introduces more hard negative samples, coming along with the heavy burden of large memory requirements. So in this paper, we propose self-contrastive decorrelation, a self-supervised approach. So given an input sentence, it optimizes a joint self-contrastive and decorrelation objective. Learning a representation is facilitated by leveraging the contrasts arising from the instantiation of standard dropout at different rates. The proposed method is conceptually simple yet empirically powerful. It achieves comparable results with state-of-the-art methods on multiple benchmarks without using contrastive pairs. So in order to learn sentence representations, the proposed approach leverages the self-contrasts imposed on the augmentations of a single sample. So in this regard, the approach builds upon the idea that sufficiently strong perturbations of the sentence embedding reflects the semantic variations of the sentence. However, it is unclear which perturbation is simply a slight variation of the sentence without changing the semantic positive pair, and which perturbation sufficiently modifies semantic to create a negative sample. Such ambiguity manifests itself in the augmented sample sharing the characteristics of both negative and positive samples. So to accommodate this, they propose an objective function consisting of two opposing terms which acts on augmentation pairs of sample. Self-contrasting divergence, which is called repulsion, the first term treats the two augmentations as a negative pair, pushing apart the different views. Then we have feature decorrelation, also called attraction. It attends to the augmentations as positive pairs. Thus it maximizes the correlation of the same feature across the view, learning invariance with respect to the augmentation. Given the opposing nature of the objectives, integrating them in a joint loss yields a min-max optimization scheme, and the proposed approach avoids degenerated embeddings by framing the representation learning objective as an attraction-repulsion trade-off, and simultaneously it learns to improve the semantic expressiveness of the representation. Due to simple difficulty of the augmentation in NLP, the proposed approach generates augmentation on the fly for each sample in the batch. To this end, multiple augmentations are produced by varying dropout rates for each sample, and we empirically observe that SCD is more robust to the choice of augmentations than pairwise contrastive methods. We believe that not relying on the contrastive pairs is one of the main reasons for this, an observation also made in self-supervised learning literature such as BYOL that I have explained this in my playlist for contrastive networks. While other methods take different augmentation or different copies of the model, we utilized the different outputs of the same sentence from standard dropout. So a key novelty of our approach is that we use the dropout for creating the self-contrastive pairs which can be utilized as both positive and negative. At last, we note that our model is different from the pairwise feature decorrelation or whitening, which I will explain this in a different video, so which encourage similar representations between augmented views of a sample while minimizing the redundancy with the representation vector. A key difference compared to this method is that they ignore the contrastive objective completely. And in contrast, our method takes it into account and provides the means to treat self-contrastive views as positive and negative pairs simultaneously. So there are three major contributions in this nice paper. First, generation of sentence embeddings by leveraging multi-dropout. The second contribution is elimination of reliance on negative pairs using self-contrast. This is like BYOL method that doesn't need negative pairs. And so the third contribution is that proposing feature decorrelation objective for non-contrastive self-supervised learning in NLP. So this is a schematic illustration of the proposed approach. And starting from an input sentence, we have two embeddings by varying dropout rate, different dropouts. So patches within the encoder indicate masking due to dropouts, and different dropout rates and resulting embeddings, color-coded, low dropout, high dropout, self-contrastive loss is imposed on the embedding. And then a projector maps embedding into a high-dimensional feature space where the features are decorrelated. And then we give it to this correlation matrix and we calculate the loss. So we create two views and the augmentation embeddings are respectively. And then to obtain different embeddings, we leverage a transformer language model as an encoder in combination with varying dropout rates. And specifically, one augmentation is generated with high dropout and one with low dropout. This entails employing different random masks during the encoding phase. And the random masks are associated with different ratios. Integrating the distinct dropout rates into the encoder, we yield these representations HI and HIB. So given the embeddings, we leverage a joint loss. So we combine these losses together. And this loss is here. So for self-contrastive divergence, self-contrast seeks to create a contrast between the embedding arising from different dropouts. Hence, this loss consists of cosine similarity of the sentences, of the similarity of samples in the batch. For feature correlation, you are familiar with this matrix. So it's a correlation matrix, which I've explained in different videos. And so the loss objective for feature decorrelation is this, and you all know we know these terms. It's a standard model, and the first term seeks to achieve augmentation invariance by maximizing of the cross correlation along diagonal. The second term seeks to reduce redundancy in feature space in feature representation by minimizing correlation beyond the diagonal. So as I said, it's a trade-off between uniformity loss and alignment loss. And of course, we want both of them to be small as possible. But in practice, it's very hard to do that.